Hello everyone. Can someone use chat to confirm that they can hear me? Okay, good. Thank you. Excellent. So it looks like we have maybe a 5-second delay streaming this way. So I'll give, when I ask questions, I'll have to remember to give lots of time. Um, Excellent, good. Everyone can hear. We have a couple of minutes. Does anybody want to ask me a question before we begin? How long does it take for the server to grade the assignment? It takes maybe 30-40 seconds. In fact, we'll do an example of submission to the server today. So you can see actually how long it takes to grade a completely incorrect assignment and a completely correct assignment. Do you need to code with me? No. Better that you don't try and type everything as I type it. I'll post the files that I create today. Why are we looking at Varney the Vampire? It's a free book that serves our purposes because it's very, very long, very, very free, and it'll let us play around a bit with some of the data structures in the Java collections framework. What does output the line L that has exactly 4,000 lines smaller than L mean? It means that you should output the 4,001th smallest line. So if you, well, yeah. Do we need to compose the file after we are done? I don't know what that means. Okay. Are you allowed to use classes that implement the interface, or do you need to implement the interface methods yourselves? No. You want to use classes in the Java collections framework that implement the interfaces in the framework. So array list, linked list, hash set, which we'll see today, tree set, those things are allowed. When will we be able to do all questions in the assignment? After today. Some people have already completed the assignment. Yes, someone is struggling because their zip is not unzipping. I've seen a couple of examples on the server, I don't know if it was yours, of people who were submitting RAR files. That's a different format. It is another archive format, but the server tries to unzip those and it is unable to, so it ends at the unzipping step. So check your file. Figure out what type it is. If you've created it under Windows, there's some chance that if you have RAR installed, you created a RAR file instead of a zip file. Just because it finishes in a .zip extension doesn't mean the format is .zip. When will we be able to hand assignment 1 in? You can now. Some people have already completed it and gotten 100%. So let's, since it's time to start, let's let's do that and see what it looks like. So if you go to the assignment 1 web page, you get a long list of instructions about grading, which people skip over naturally because they're boring to read. There's some details of what it looks like when you what the sample file looks like, the zip file that comes with assignment 1, a link to the zip file itself, and a link to the submission server. So if you click on the link to the submission server, you get to this page. It asks you for a secret key. If you don't have one yet, you click on this link to get it. You'll have to enter your student number, and your secret key will be emailed to your Carleton email address. If that doesn't happen within seconds, then look in your spam folder. Sometimes those emails get classified as spam by the Carleton server. So get your secret key, paste it in here. It's a huge long string. Keep it secret, because if you don't, nothing terrible can happen except that someone can submit an assignment on your behalf. There's not much danger in that unless they've submitted something which is obvious plagiarism, in which case you could get in trouble for plagiarizing someone else's assignment. What is Varney the Vampire? It's a long book full of words that we just need a big source of text for one of the examples we're going to do today. All right, so you get to this assignment submission page. Maybe you have done the assignment, or maybe you haven't yet. But even if you haven't done it yet, you can still already do this. Here's the zip file that I got from the assignment web page, completely unchanged. I haven't done anything to it, but I'm allowed to submit it. So I submit, and right under the submit button there's a note that says be patient. There you go, it's done. So it unzipped things correctly. It removed any extra files that are not needed. So part0.java is part of the zip file. The server doesn't want that, so it gets rid of it. And then it compiles part 1, and then it runs a test on part 1, and it fails, of course, because nothing is implemented in part 1 yet. And the same thing happens with parts 2, 3, 4, 5, and 6. And so I get 0 out of 50 for this submission. So question is, what are the input and output files for the assignment? On the assignment web page, there are sample input-output files for every question. You can look at those. And in particular, you can use the sample input files to see if you're getting the matching output. I'm not going to tell you exactly what the files are on the server, because if you do your implementation correctly, it should work with any files. So if you're failing on something on the server, you need to do more testing. Okay, so that's an example of a bad submission. If I go back, I can submit a different file. In this case, it's one that I've completed, and I submit it. Again, I have to be patient. Yes, you have unlimited attempts for submissions. So even though I just got 0 on this submission that I made just before this, hopefully this one will do better and I can get a better than 0 mark on the assignment. So you wait a little while. This is taking longer because it's not failing the tests immediately, and it's running all the tests. And here it ends up removing some extra files, because in my zip file I included the Java class files, which are the compiled files. Server doesn't want those because it's going to compile on its own. It's harmless to include them, but it just makes a note that they're not being used. And it passes all of the tests, and I get a mark of 50 out of 50. This output, in both cases, whether you pass or fail, gets emailed to your Carleton email account, the one that you received your secret key at. After submitting, will your grades show up on CU Learn? No, that won't happen until sometime after the assignment is due, because well, there's no point updating, adding intermediate marks on CU Learn. So you know what your marks are because you've submitted. You have email records of all these things. And remember, the rule is you will get the highest mark out of any of your submissions. So even if you muck something up and somehow break something and get a mark of 0 very close to the deadline and aren't able to fix it, if you submitted something reasonable before that, you'll get that mark. The one thing to be very careful of with that is it means every submission counts. In particular, if you copy someone else's submission or copy someone else's submission or copy something off the internet, then you run the risk of getting in trouble, even if that's just your intermediate submission, even if it's one that you weren't planning on making your final submission, because it's graded like all the rest. Is the secret key emailed to you already? No, it's not. You click on this link here that says get your secret key. Okay, so that's how you submit an assignment. You zip up a file. A few more of these sort of mechanical things that we want to do. Let's take a look at the assignment itself, or the zip file that comes with it. So here, a little bit hidden by me, right here is the zip file that comes with the assignment. So what are you going to do with that zip file? Well, you should unzip it. I do this from the command line, but you can do whatever works for you. So that creates a directory called COMP2402A1, and it has 11 Java files in it. I can compile those. So that directory right now is living in whatever directory I unzipped into. Okay, so staying in that outer directory, not going into the COMP2402A1 directory, I want to compile every Java file in there. That's done. And if I look in there now, there used to be only Java files, but now for each Java file, there's also a class file. That's what compiling does. It takes your Java source code and turns it into JVM bytecode. That's what's in the class files. And if I want to run one of those programs, there's only one right now that does anything. It's the example code in part 0. So in this assignment, everything lives in the COMP2402A1 package. So everything has to be prefixed with COMP2402A1, and then the class name that you want to run. So I run part 0. I didn't give it any arguments, so it's actually waiting for input from standard input. So there's some input, and I'll terminate it under Linux. It's just by pressing Control D on a blank line, and then it does whatever it's supposed to do. In this case, part0.java just reads everything into a set and then prints out the set. So the first lines, that's these ones, they were the input that I typed in. After that comes the output of the program, including the execution time. Okay. So since it reads things into a set, remember, sets don't remember order, they don't care about order, so they get printed out in a different order. All right, so let me look at a few questions. You're on Windows, then I can't help you. Other than to say use PowerShell, make sure your Java programming environment, your JDK, is set up so that Java and Java-C are in the path. Otherwise, actually, things work basically the same. The end of file character, when I pressed Control D under Windows, is something else. Maybe it's Control Z. Is it CMD? No, CMD is an ancient terminal under Windows. Use PowerShell. Just hit the Windows key and type PowerShell. It'll open it for you. Even if you change the directory to COMP2402A1, do you have to prefix it? Two things. Don't change into that directory. So if I change into that directory and I try and run part 0, it gives me an error. It says that it can't find a class called part 0. And so don't do that. Run it from outside, one directory up. In Java, the whole package hierarchy is mirrored by the directory structure that things are in, and so the directory that you're currently living in is the top level. If you want to access a package on the file system, that should be in a directory that's named the package name. Okay. All right. Is it necessary to write the solution under the Linux system? No. You only have to use Java under any system that you like. Java code is portable. Okay. So there's an example of how to compile the stuff in the assignment, and a quick example of how to run. Now, it's awkward to constantly be typing in inputs all the time. So if you like, instead, you can take the sample files that are available on the assignment webpage, the sample input and output files, and you can run on those. So well, let me look at what this file is. So that's a sample input file that I got from the web page. It's just a list of a few words. So I can run the program part 0, and if I give it one argument, which is the name of that file, then it will read from that file, but it will still print to standard output. And if I give it 2 arguments, if you want to work with really big files, then even printing them can become burdensome. Then I give it 2 file names. Be careful with the second one, because it's going to clobber it. If it doesn't exist, it's going to make that file and it's going to write to it. And if it does exist, it's going to clobber it. It's going to destroy it and write over it. Okay, so this command here says read from part 1a.in and write to part 1a.out. And then all you see is the execution time. And if I look in part 1a.out, I'll see the output there. Can I scroll up? Very briefly, and then later you can look at just look at the playback. Okay. What version of the JDK are we officially using? Any semi-recent version is fine. We're not doing anything that's going to run into to real problems with the JDK. If you're using a really new one, don't use any of the sort of very new Java language features, but there's not many, and for this assignment you really don't need to use much. It's just the Java collections framework, and it's been the same version of the framework for the last 10 years at least. Okay. All right, so that's the sort of mechanics of doing this. If you want to do this in a IDE, then probably you'll need to figure out how you specify command line arguments to your Java programs, and that's different for every IDE. You can ask other people who use the same IDE. Do you know how do we switch to the index/tmp? You mean which directory? How do I get into that directory? That's just the cd command. Okay, so I I don't want this course to be a course about using shells. If you don't like using shells, just figure out how to use the IDE to do what you want. And I also can't support every IDE, but you guys can support each other with that stuff. You can ask questions from your friends, and I mean there's hundreds of you, so you can really get this to work. Okay, good. So I have here let me see where it is, a file open that I wanted to show you. Because it sort of wraps up what we were doing last class a little more quickly. There we go. It's there we go. So we went over the various implementations for most of the interfaces last class. So we looked at the two implementations of list, which were array list and linked list. This is available on the web page. You can look at it. The main differences between those two were that array list was really fast for get and set, and it's really fast for adding and removing at the end of the list, but adding and removing near the front of the list or anywhere but the end of the list takes a long time. Linked list, on the other hand, is really fast for doing anything at either the front or the back of the list, but it's the further away you get from the front or the back, the slower it gets. So there's the running times of the operations there. We mentioned that deck, basically there's two implementations of this deck class. But remember, and this we'll sort of forget about decks as the course goes on, because decks are really just a restricted kind of list where you're only allowed to add and remove from the ends. And we saw that linked list already lets you do that. So linked list implements the deck interface. It's just a really thin layer over it. And there's another class in there called array deck, which uses a technique called a circular array to also do those things efficiently. So if you really want to use the deck interface, great, you can do that, and both of these classes implement it efficiently. But also feel free to use the list interface, and just make sure that you use a linked list if the operations you're doing are adding at one end and removing from the other. That's just as good. Let me get my chat window open so I can see if anyone's asking anything. All right. As for JDKs, yes, OpenJDK is still free. There are lots of JDKs that are free. You can use OpenJDK. I mean, I think the Java development kit from Oracle is still free. There's no issues there. You don't have to pay for Java development environments. Okay, so that's deck. Queues, we saw that an array deck can implement a queue, at least a first in, first out queue. That's where you just add at one end and remove from the other. A linked list also does that because it allows that. I didn't mention this operation. It's called element, which just tells you if I was to remove something from the queue right now, what would that thing be? So it kind of looks at the next thing in the queue without actually removing it. All those operations run in constant time using array decks and linked lists. And that's just because they're list operations that only operate on the two ends of the list. And then there's another kind of queue called a priority queue that's available to you that lets you add and remove in log n time and look at the smallest element in the priority queue in constant time. Now, that is different than the other two implementations because it's using the priority queuing disciplines, which always removes the smallest element from the queue. Okay. For sets, there are the main implementation is the hash set implementation. It's very cool because you can add anything, you can remove anything, and you can check if it's in the set in constant time. So it doesn't matter how big the set is, it always takes the same amount of time to add or remove something from it and to check if something is in there. And it does this basically by taking whatever it is you're looking for and hashing it up, means chopping it up into bits to turn it into an integer, a random looking integer, and it uses that integer as an index into an array. And either the thing you're looking for is stored at that index in the array or it's not. But in any case, there's only if anything, there's only a few things at that index in the array, so it finds it in constant time. There's another implementation of set, which is tree set, which actually does more than implement set. It implements the sorted set interface. It's a little bit slower. It takes log n time to add and remove things. That's not really noticeable in practice, and it supports the sorted set operations, the head set, tail set, and subset. We'll go over an example of those today. And then there's two implementations of map and sorted map, and they are hash map does everything in constant time, and tree map does everything in order log n time. And those are, remember I said that maps, ultimately they're maintaining a key set, a set of keys that map onto values. And so the same data structures that are used to maintain sets, it's the same technology that's used to maintain maps. That's why there's a hash map and a tree map in exactly the same way that there's a hash set and a tree set. Okay. And there are a few sort of convenience things, and I encourage you to take a look at the Java Collections framework. We're only just touching on it here, but there's a class in there called collections, not collection, so collections with an S, that is just a bunch of static methods. So those are the things that in other languages you might call procedures. They don't operate on they're not instance methods for an object. They're just plain static methods. So for instance, collections.sort will take a list and sort it. Collections.min or collections.max will give you the maximum or minimum value in a collection. There's collections.reverse that will turn a list into reverse order. And there's collections.binary search, which if you give it a sorted list, it will do binary search to find some element in there. Okay. All right, what about stacks? There is a stack in Java. I don't think it implements, stacks naturally fall into the queue interface with the last in, first out queuing discipline, but I'm not sure that they have done that in the Java Collections framework because there was a stack class introduced into the Java libraries before the Java Collections framework existed. So for historical reasons, that's stuck there. But again, I don't want you to think too much about decks and stacks and first in, first out queues, because all of that is covered by the list interface. Right? All of those things are just add and remove with the index 0 or the index n-1 or n. Okay. So any quick questions about these things? If you want details, just wait, because we'll actually be coding up a bunch of these things and using them. Okay. All right. Let's get rid of that. Uh-oh. Ooh. That was close. Are people still there? Are we still broadcasting? Okay, good. There was a big X server crash there. Good. It wasn't clear that that was going to survive. All right, so let's do a few examples for the people who haven't started the assignment yet. I realize just talking about these classes abstractly for some people is difficult. They really want to see code. So let's do that. Here I've created a class called listDemo. As always, the class has to live in a file whose name matches the class name. So it's in a file called listdemo.java. And it has the usual public static void main string args. That's something you need if you want to make a class runnable. And I just threw in a bit of code to read args, that's the command line argument, because I'd like to be able to specify an integer for maybe running tests on bigger or smaller size. Okay, and then I just created an array of names just so we have something to play with. All right, and here I imported java.util.list. Remember, that's the interface, so that's in there. Java.util.ArrayList, that's the array-based implementation of the list interface, and linked list, the linked implementation, the node-based implementation. So how do we create one of these things? Well, if I want to make a new list, I have to declare a variable for it. And all of these classes, these data structure classes, the ones that hold objects, they are generic, meaning that they have a type associated with them that is the type of objects that they're willing to hold. So I want to make a list that contains strings. I'll call it DS, and that will be, let's make it an array list. Okay, so this tells me I want a variable called DS that contains, that variable is a list of strings, and I initialize it with a new array list. And Java is a little bit smart. I don't have to specify again that it should be an array list of strings. I can just leave this generic parameter blank. Java is smart enough to figure out that because the thing on the left-hand side is a list of strings, that this should be an array list of strings. What's the point of importing those things separately? It's good practice in Java to import really the classes that you need. When you import java.util.star, that's a huge number of classes, and for little things like this, it's not such a big deal, but for a larger project, you risk running into a name conflict, possibly later on, right? Because when I import java.util.star, that means that every class in java.util becomes a name that's now used in my code without qualifying it with java.util, and maybe I'll want to make my own class. Maybe at some point in the future, java.util will contain a class called listDemo, and then I'm in trouble because I have 2 listDemo classes in this scope now. Should we always have the interface on the left side? It's good practice to specify on the left side that it's just the interface for no other reason than if you want to change the implementation later, it's super trivial. You only have this to change, right? I could change this right now to linked list and it would just do the same thing, but initialize it with the linked list. And when you have, you specify this thing as being a type of list, that means you're only allowed to do operations on it that the list interface supports. So even though ArrayList has some other little of its own operations, you're not allowed to use those because they're hidden by the fact that DS is just a list, so it can only use things in the list interface. All right, so let's just check that compiles. So this is called listDemo. Great. Compiles, but doesn't do anything yet. So let's have it do something. So we already have an array of names. So let's iterate over each string S in that array of names. Let's add it to our list. And then we'll print it. There's an old version there. I know what's happening. I moved a file and the editor followed it. Okay. All right, good. And there's the error. I wrote name here. I should have written names. Okay, so created a list DS. I iterated through this array of names and I added each of them to the list. This is the add argument. Sorry, this is the add method that takes only one argument, the thing to add. And when you don't specify, when you use the one argument version, it adds it to the end of the list. So that means that Seth was added first to the empty list, and then to the end of that list, Phil was added, and then Sam, and then Fabio, and then Bobo, and then Tom, in the same order that I iterated over them. If I wanted to reverse that order, I could add at position 0 instead. And then things come out in reverse order because the first thing that gets added is Seth, and then Phil gets added before Seth at position 0. Now there's a list with Phil and Seth, and then Sam gets added before Phil and Seth, and so on. Okay, so there's a it's an example of adding at the front. If you constantly add at the front, you will actually reverse the order of the things you're adding. Okay, good. Now I can add anywhere I want in the list. So for instance, at position maybe 3, I can add Nate and see what that gives. So this is the list before I added Nate. At position here 0 is Tom, 1 is Bobo, 2 is Fabio, 3 is Sam. So when I add Nate at position 3, it takes the place of Sam and displaces Sam to position 4, Phil, and then Phil and Seth get moved as well. Okay, that's clear. You can ask me questions now. Okay, good. All right, and in the same way that you can iterate over elements of an array, you can iterate over collections in the Java Collections framework. So for string s in ds, so this is an iteration now over the elements of the list. And that'll just print out the elements in the order that they appear in the list. Isn't it more efficient to just print them in reverse order? Yes. If this was a long list, this would be very inefficient code, and we'll see that in a second. I just changed the order so that you could see an example of an add operation that doesn't add at the end. So the 2-argument add operation. And we can remember there's a remove operation on a list. So if I don't like Fabio, let's say, I can remove him. And there it was before I removed him. So from that list that's highlighted, I removed the element at position 2. That's Fabio. 0 for Tom, 1 for Bobo, 2 for Fabio, and then he's gone. Okay. Add, remove, and I guess the other thing you can do is set. So let's change Nate. Or let's change, let's change Nate. So Nate's now at position 2 to Harry. Okay. Forgot to print it out. So there's the set operation that changes Nate to Harry. Okay, so all sort of straightforward and easy stuff. Let's now let's do some bigger things. I don't need that cluttering up the output. So let's create a big list so we can see something about performance. And for that, I don't want a list of strings. Let's make a list of integers. let's see if that compiles. In general, any 5 lines of Java code that I write without compiling will not compile immediately. There we go. So we run this, and it says adding 10 values. That's what's happening here. It prints adding 10 values, and then as soon as it's done, it prints done. That was instantaneous for us, so that's good. And what if we change 10 to 100? Maybe that'll be slower, still fast. 1,000, still fast. 10,000, 100,000, 1,000,000, 10 million. 10 million, I don't know what the frame rate's like there, but there was like a slight pause there. What does flush do? When you use system.out to print and not print a line on some systems, then that whatever you printed does not appear right away until either you flush system.out or you finally print a new line on system.out. So flush is what allows us to, let's say we go up to 80 million. That's why we can see this printout that says adding 80 million values with dots, and then we see that immediately until it's done and prints the new line. Without flush, it might not have, you might not have seen that. Okay, good. But even at 80 million values, this is really fast. It's like a second or two. So let's try and measure this a little more carefully. So let's set up a timer. And let's only time exactly what we want to time, which is the time it takes to add those values. So that's when we start the timer, stop the timer as soon as we're done, and calculate the elapsed time. So system.nanotime gives you time in nanoseconds, which is 10 to the 9 seconds. So we have to multiply by 10 to the minus 9. And we will show how many seconds that took. So for 10, it's almost nothing. Let's try 1,000 elements. Okay, that's still almost nothing. We don't even get to see it. 10,000, good. For 10,000, it takes 0.0027 seconds. For 100,000, 0.0068. For 1,000,000, still only like 3/100ths of a second. And for 10 million, 1/3 of a second, roughly. And 100 million takes like 3 seconds. Okay. So that seems to make sense, right? Especially this jump as things get big. So 0.3 seconds to do 10 million values, and sort of 3 seconds to do 100 million values. It's about 10 times longer. And the same thing here. When we jumped from 1 million to 10 million, that was an order of magnitude, so about 10 times longer. That agrees with the fact that adding to the end of a list, an array list, takes constant time, And so if we add 10 times as many things, it should take 10 times as long. Can I scroll up the code? What is my CPU? That is my CPU, an i7-4790K at 4 gigahertz. Yeah. So if you miss something, go back and rewatch it, or indeed just rewind the stream. You can still continue to watch it. The only issue then is you can't really ask questions because you're not on the live part of the stream. But whatever you need, or ask a specific question. I don't want to keep scrolling back to stuff that I've done previously. What is n? N is an integer that I read from the command line. So by default n is 10, but if there's a command line argument, and indeed there's one right here, that becomes the value of n. Okay. All right. So that's fantastic. This thing is an array, and that's 100 million values in like 3 seconds, really fast. But remember, this thing is an array list, and if we remember about the performance of array lists, the running time was of adding at position I is 1 plus n minus I. Here we're adding at the end, so in this case the position that we're adding at is always n. It's always the number of elements currently in the array. So that means it runs in constant time per operation. So n minus I is 0. But we can make lives harder for ourselves and try doing it the other way. So first we'll empty our list and start fresh. And we'll add the values at the front. So instead of adding always at the end, we will add at position 0. So now it's at the front of the list. We'll compile that and do that with 100 elements. Okay, that adding 100 values at the end was very fast. Adding 100 values at the front was also very fast. Looks comparable. In fact, it looked even it's even faster to add them at the front. Let's try 1,000 elements. Still very fast in both cases. A little bit slower to add them at the front, maybe like twice as slow now. 10,000. All right, so here again, it's like twice as slow to add at the front, right? 0.002 versus 0.005, or 2.5 times as slow. So you might think, okay, adding at the front is slower, but it's only maybe twice as slow. So let's go to 100,000. All right, there's a more significant jump from 0.007 to 0.5. So now it's like 100 times slower. And if we jump to 1,000,000, adding at the front really takes a long time now. And that's because, remember, adding at the front of an array list requires that you shift everything that's already in the list over by one position to make room for the thing at the front. And that's still going. So adding at the end took 0.027 seconds. Adding at the front is still going many seconds later. And this is not an infinite loop. It's just a very slow algorithm. Okay. So, and this is something that you'll see on the assignments if you do an inefficient implementation, so something that does something like this, then your implementation may be correct. It may give the correct answers, but the test server does test on files with 1 million input lines. And so, and on the other hand, the test server is not willing to wait forever and use up resources running your program for any length of time. It only gives about, I think, a limit of 5 seconds for any program to run. And so it would have killed this already, and you'd get an exception that says, you know, either your program crashed or it took too long to run. You can usually tell if it's that it took too long to run because it happens on the later test files. So for instance, like test file 4 and test file 5, those are typically the big ones, 100,000 and 1 million elements. So the difference between adding at the end and adding at the front was 3/100ths of a second versus 90 seconds. Okay. So not a small difference. Now, of course, if you really wanted to do this, if you had a good reason to add at the front, well, then an array list is not the right structure for you to use. Instead, you can use a linked list. Because remember, a linked list is very happy to add and remove at either end. And there you go. So that's the difference. That's delete 5 letters and add 4 letters. So replace array with linked. Add 6 letters. Replace array with linked. So all that was one word in my code that I changed, and it dropped the running time from 90 seconds to 4/100ths of a second. And that's why it's important. Well, it's important to know these things. And even though in your day-to-day programming job, or in most people's day-to-day programming jobs, they don't find themselves implementing data structures like lists and things every day, but they do use them constantly, and you need to know how they perform, so you don't do something silly like add 1 million elements to the front of an array list and wonder why it's so slow. Here's something else you should not do. So now that we've got the adding working well, let's try something silly. So I've got my list. It's all filled up now with n numbers. They happen to be in reverse order now, but that doesn't matter so much. And now I'm going to do something that lists weren't designed to do. I'm going to go searching in the list. I'm going to keep asking for a bunch of numbers. Does the list contain this number I? And right now it's a linked list. Wouldn't matter if it was an array list. Lists aren't designed for that, but they're not designed to be efficient at that. And so, if I do this with 1,000 elements, yeah, looks fast. 10,000 elements, Oh, well, that's already slowing down quite a bit. 100,000 elements, and it's painfully slow. Okay. So, so again, don't use the data structure for something that it's not made for. I'll just kill that rather than wait for it. So let's do something similar with sets. So set demo class, and here we'll illustrate set and hash set for now. There's a list of names. We put them all in a, we iterate through the list and put them in a hash set, and then print that. Let's just see what that does. So we put the names Seth, Phil, Sam, Fabio, Bobo, and Tom into this hash set, and then we print it. Looks similar to what happened before with the list, except that the order is different. We put them in this order: Seth, Phil, Sam, Fabio, Bobo, Tom, but when we print it, it comes out in a different order. And that's because sets don't care about order, or a set is considered to be an unordered thing, so you can't rely on things appearing in any particular order in a set. You just rely on sets doing 3 things quickly: adding, removing, and checking if something is in the set. So we'll check what add and remove, how that works. So this is the add operation when I add Nate to the set. In this case, it happens to go at the front, but there was no guarantee that it was going to work out that way. And when I remove Bobo from the set, it disappears. The remaining elements happen to stay in the same order, but there's no guarantee about that either. Can somebody type something just so that I know that people are still alive? YouTube seems to think that, good, great. YouTube still seems to think that this is an excellent connection. All right, and so we can ask if a set contains something. Let's see if it contains Phil. And let's see if it contains Bill. So contains Phil returns true, because there's Phil right there in the set, but contains Bill returns false, because Bill is not in the set. Okay, good. Now, if we wanted, we could take our hash set and instead use a tree set. So remember, a tree set is the thing that implements the sorted set interface. Let's remember to import that. And now everything behaves more or less the same way, except that because tree set is really a sorted set, we can rely on the things when we iterate over them in the set that they'll come out in sorted order, right? And in this case, sorted order is the sorted order for strings, which is just lexicographic comparison. In this case, nothing too weird happens because it's all names. The first letter is always capital and the other letters are always lowercase, so it's what you'd expect, but it's a case-sensitive comparison. So uppercase characters and lowercase characters compare very differently. In particular, let's see. I've forgotten how ASCII works. We put zebra in there. Not remove, add. Okay, so lowercase comes after after uppercase. So anybody with a first name, even Alan, will come after all of these people who have a capital letter in their first name. All right. So we can do these same kind of performance testing we did for the other, we did for lists. We add a bunch of things. So that's add n elements to a sorted set or a hash set. And then we can go through and check if the hash set contains those, contains a bunch of elements. So if you look carefully at this code, you see that we add a bunch of even integers. They're I times n, I times 2 for I equals 0 to n minus 1. And here we search for a bunch of integers, both even and odd. So of course, when I do this for only 10 elements, it's always going to be fast. So let's do it a more interesting test, maybe 100,000 elements. No problem. Adding them all only took 2/100ths of a second, and searching for them didn't even take 1/100th of a second. 1,000,000 elements, still really fast. 10 million. There's a noticeable pause there. In particular, the adding took nearly a second. And so that's 10 million. So if we go up to 100 million, then if it took nearly a second to add, yeah, so 0.8 seconds to do 10 million, 8 seconds to do 100 million. So indeed, it's about to add 10 times as many elements and search for 10 times as many elements is about 10 times slower. Really, really fast. Okay. Anything else? I guess we could compare. So we saw we could do the same tests again, but this time instead of using a hash set, we'll use a tree set. See what that does to the performance. First error blew up. Identifier expected. Oh, it's outside of the function. Maybe not such a big test. There. So these first two results are with hash sets. So that's not the sorted set, and they're fast. This is with the tree set, which is a sorted set. There's a price to pay for that. It's slower, but it's not outrageously so. Okay, good. And for assignment 1, this gives you some idea of what kinds of things you can do. What kinds of things you can do and still not run up against the server's time limits. So the fact that there are test files with 1 million lines in them is not a problem if you use the right data structures, right? The things that we did that had 1 million, 1 million operations, they happened in like 1/10 of a second, or like in the worst case, a half a second or something. So use the right data structure and you'll be fine. And use the wrong data structure and you don't have a chance. So it's not about optimizing some really small, tiny little constants and choosing really specific machine-specific things. It's really about using the right or wrong data structure, or just doing too many operations. So you have to think about how long things are going to take, and use that table that I showed you at the beginning of the class that tells you for each of those data structures, in fact each of those implementations, how long does each operation take, and decide if that makes sense. If you have an operation that takes order n time and you're doing it n times, that's not so good. Tree sets and hash sets don't sort. Tree sets do sort. Hash sets do not sort. Hash sets maintain things in an order that's convenient for them for doing lookups. Tree sets keep things in sorted order. Yes, I will upload the code on the course webpage. Look at the section of the webpage that goes along with today's lecture. I'll add both of those files. Okay. I think. Okay, so now we get to Varney the Vampire. So let me just compile this thing first. Uh-oh. Okay, so there's a file here with a bunch of stuff in it. It actually began from one of the assignment files. So it opens a reader and writer. That's not terribly important. But there's some code in here that opens a file and parses it into words and returns all of those words as a giant list of strings. So that's called slurp in here. don't worry about how it works. We just want it so that we have a big chunk of data to work with. And that is why we have this, we're interested in Varney the Vampire, which is a book written in the 1930s. It's a pulp fiction book, so back when the value of certain books was swayed by like how many pages they had or how many words were in them. But the important thing for us is that it's copyright free and it's freely available, so we get to do whatever we want with it. And in this case, it's just to use it as test data. So if I run this thing with varney.text as an argument, then let's look at what is happening. So we run this thing and we slurp the entire contents of varney.text, which is how many words are in Varney? 332,188 words that are contained in there, and we get that as a giant list. And here, of course, I don't want to print out the entire contents, so there's just a little helper function that's also included in this file that will grab the first 20 elements, or first whatever number of elements of a list, just to print them to make sure that what we have makes sense. And indeed, the first things in here are, well, there's an empty string, then the project Gutenberg ebook of Varney the Vampire. So each of those things is a word in the list. That's the first 20 things in this list. And then we can count the number of words, which is just the size of the list, 339,036. It looks like whatever we're doing to count words is slightly different than what Unix's word count does. Probably it's counting things like punctuation and stuff as well. We're stripping those out. Okay, so, well, what do we want to know? What's the useful information we can gather with the data structures we have? Well, it's nice that the author wrote a long book, but you might be curious about the author's vocabulary. So, you know, just because they can write a little long list of words doesn't mean that they know a lot of words. Maybe they're just reusing the same words over and over. So we can see how big the author's vocabulary is. Let's try that. So if we want to know the author's vocabulary, that means we want to know how many distinct words that they've used. And for that, a list is not the right data structure, but a set is. So we create a hash set, and there is a one-line way to do this, but I'd rather just show you guys iteration. You guys can look for collections.addAll if you want, which does this basically in one line. So I want to iterate for every word in my word list. I want to add it to my word set. Now that means that if the same word shows up twice, 2 or more times in the word list, the second and subsequent times that I try and add it to the word set, nothing will happen. Okay. So at the end of this process, the size of the word set is actually the number of distinct words, or the vocabulary size. Variable w is already defined, so let's not use that. So 339,000 words in the book, but only 12,079 distinct words. So that's not a huge vocabulary. Right, I don't know if you know of this, this text editor called the Upgoer 5, which is a text editor that only lets you use the 10,000 most common words in the English language. And it's actually surprisingly difficult to use. If you restrict yourself to only 10,000 words, there's a lot of things that are difficult to express. It's sort of invented by the author of XKCD, who tried to explain the operations of a rocket in using only those 10,000 most common words in the English language, and that's how you end up with things like, you know, the Saturn V becomes the Upgoer 5. It's the thing that goes up, and it had the number 5 in it. So 12,000 is not a huge vocabulary. So although it's pulp and bulk fiction, it's maybe not quality fiction. So I mentioned that there's this collections class that has a bunch of routines in it. So if we wanted to, we could shuffle our word list. And that basically just randomly permutes it. And then we could ask for, after randomly shuffling like that, we ask for the first 50 words. We'll get a random sample. And you see, as you'd expect in this random sample, common things come up. To, he, and comes up more than once. He comes up many times. A, so what you'd expect from a random sample. And I'll finish very quickly by looking for what are called anonyms. So these are words that are the reverse of themselves. So how would we do that? Well, we should iterate over all the strings. And we don't need to go over everything in the list because we already have a set that tells us all the unique strings. And I want to know if the string S, when it's reversed, is also in the set. So that would be if the word set contains what is the method for reversing a string? I'll see if it's s.reverse. Probably not. Yeah, let me just quickly look that up. Reverse string. Why is that not working? one more way. Okay. Okay. So that didn't seem to work, but we're out of time. We'll maybe spend 5 minutes next class working on just finishing this up and looking at an example of using a map to do frequency counting. Okay. Oh, s dot reverse string. Let me just quickly check that. I'm teaching right now, buddy.
Do you know where the black tablet is? I need the black iPad.
Okay. Anyway, we'll pick this up next class. Thanks for tuning in and actually sticking around overtime. See you soon.